this one. Okay, so this kernel is a symmetric kernel. Do you agree this? Okay, so sin x plus t is a symmetric kernel. If you take this kernel, suppose I take this kernel k x comma t is into x square t cube plus 1, and if I interchange t to x to t, then we will write here t square x cube plus 1, and you can see that this quantity is not equal to this quantity. Okay, for real valued conjugate will be removed. Okay, and you can see that here x comma t is equal to comma k into x. Okay, so it means that, sorry, not equal to x, so it means that it is not symmetric kernel. Okay, only this one is a symmetric kernel. It is clear? It is clear?
Yes, sir.
Okay, and next one is the separable kernel, and also it is called the degenerate kernel. So, okay, or we can say that if a kernel can be written as the sum of the two functions gi and hi, gi and hi, basically it is t here. Okay, here if the kernel kxt can be written as the product of two functions, and one is dependent on x and another is dependent on t, then that kernel is called the separable kernel or degenerate kernel. Okay, here it is the example again. Here k xt is equal to sin x plus t. Okay, and you can write this function sin a cos b plus this one. Okay, so here you can see that this function can be written as the sum of these variables. Okay, this is a one function, it is another function. Again, here it is a function of x, so you can say it is gx1. Okay, it is h1t plus it is g1 g2x, it is h2t. Okay, so here this one is a separable kernel or a degenerate kernel. Same here, this function, if kernel is kxt is here and it is x cube into t is, sorry, x square into t cube, and you can see it, you can take it is gx function, it is ht function. Okay, it is a product of like this way. Okay, so both are separable kernel or a degenerate kernel. Do you agree this?
Yes, sir.
Okay, now, so basically these are the basic definitions which will be used to prove our result or to solve the integral equation. And second one is definition is the iterated kernel. Iterated kernel for Fredholm integral equation of second kind. Okay, so we will find the iterated kernel for Fredholm integral equation of second kind only. So do you know what means of second kind? Second kind means a differential integral equation into this form. Yes. Second kind one, this one means Vx is 1 here. Okay, then that equation is a second kind Volterra integral equation. Volterra means fix, sorry, Fredholm means fix the limit. Okay, so here we have second order or a second kind Fredholm integral equation, and their iterative kernel will be here x1. It is the first iteration of kernel kxt, which is given in the Fredholm integral equation, and it is equal to the itself of that kernel, means x1 xt sorry, k1 x comma t is equal to k xt, and its kth iteration will be equal to friend integral a to b, because it is the Frendelov integral equation here, a to b k xz kernel, this kernel which is in which we have replaced z from t, and k minus 1 iteration of the kernels, means kn minus 1 zt into dz, where n is 2, 3 up to n. Okay, if you put here n equal to 2, then we will obtain like this way. If k2 xt is equal to a to power ab k xz and k1 zt and into dz. Okay, and we know about k1 zt, this one is the k1 xz. Okay, just we will how to find x, how to find this one, z into, just replace x, replace z in place of x, replace z in place of x, then we will obtain k1 zt. Okay, so basically this is the iterative nth iteration of the kernel. And for the Frendelov integral equation, just remember this, the fixed limit are fixed. Same here, we have a iterative kernel for Volterra integral equation of second kind also. Okay, same condition is here. K1 xt is equal to k xt and knx comma t is equal to, here lower limit is t. Remember that, because in the Volterra integral equation a to x. Okay, but in this case the lower limit is t, upper limit will be x variable. Okay, upper limit will be variable here x, and kxz and kx minus 1 ztz for n equal to 2, 3. Okay, same here, if we find k2 xt, then it will be here limit t to x k xz k1 zt dz. Okay, and here k1z is this one. From this one we can calculate k1 zt, means this quantity can be calculated from this one, this expression. Okay, or this expression. Do you agree this? Any doubt? Can we proceed?
Yes, sir. Yes.
Okay. Okay, so basically we have two types, iterative kernels. Iterative kernel for Frendelov integral equation of second kind, and iterative kernel for Volterra integral equation of second kind also. Okay. Now we have another type of the kernel that is called the resolvent kernel, and resolvent kernel, or also we can say it is reciprocal kernel of first boy Frendelov integral equation of second kind. Okay, means resolvent kernel, or also we can say the reciprocal kernel for Frendelov integral equation of second kinds. Okay, so suppose the solution of Frendelov integral equation of second kind is defined here. It is the solution. It is the solution of Frendelov integral equation of second kind. This one is the solution. Okay, where solution is ux equal to fx plus lambda a to b, because it is Frendelov, rx t comma lambda ft dt. So here the function which is included into the integral term, means integrand, that will be called the resolvent kernel. Okay, it is called the resolvent or reciprocal kernel of Frendelov integral equation of second kind. Okay. Same here, we can define the resolvent kernel or reciprocal kernel for volatile integral equation of second kinds. Again, suppose it is a solution of volatile integral equation of second kind. Here, this one ux equal to lambda x plus ux plus lambda it a. You can see here it is volatile integral equation, so a to x is given here, and gamma x t lambda f t dt. Okay, then this kernel, basically it is a kernel. Okay, this is called the resolvent kernel or reciprocal kernel for volatile integral equation of second kind. Is it clear?
Yes, sir.
Okay. Now, eigenvalues problem for integral equation. Okay. So, first of all, you know what is the eigenvalue problem for matrix, and you know that if A is a square matrix and lambda is a any scalar and x is a any non-zero vector. Okay, so what is the eigenvalues problem? Means ax is equal to lambda x. Do you agree this?
Yes, sir.
Okay, ax equal to lambda x, and also we can write this equation like this way: a minus lambda I into x is equal to 0. So basically it is not, it is the homogeneous equation in x, where x is the vector, lambda is any scalars, I is the identity matrix. Okay, a minus lambda I dot x equal to 0. So it is a homogeneous equation in this case. Okay, and for non-zero x, if there exists a lambda such that this condition satisfied, then we can say lambda is the eigenvalues and x non-zero vector is called the eigenvector corresponding to eigenvalues lambda and of A. Do you agree this?
Yes, sir.
Okay, so here what can we use? So in this case, it is a homogeneous pendulum integral equation. Do you agree this? Yx equal to lambda a to b k x t y t dt. It is homogeneous. Do you agree? It is also homogeneous. Okay, and this equation is also can be written as, do you know this equation can be written as lambda I minus a dot x is equal to 0. Can I write this one? Okay, suppose let a to b kx comma t into dt is a operator. I can write this operator is by capital I here, I writing j here. Then this expression can be written as yx is equal to lambda j into yt. Okay, where j is this one integral operator. Okay, j is integral operator. Do you agree this? So this equation also can be written as 1 minus lambda j dot y is equal to 0. Can we write this one? Can I write? Can I write? Now compare this equation, this is and this equation. I think these are same. Here A is a matrix. Matrix is nothing, it is a one type of operator. Here again, and we also you can write here. Okay. So again, here lambda is nothing. Lambda is a scalar and j is a operator here. So it means that, and y is a function. For y equal to x not equal to 0, if y is not equal to 0, if there exists a lambda, then we can say lambda is the eigenvalue corresponding to the eigenvector y. Do you agree this? Am I right? Okay, so basically we can say that the value of parameter, I'm erasing all these things. Okay, so here value of the parameter lambda for which the equation has non-zero solution, means y is not equal to 0, then lambda is called the eigenvalues or kernel of the kernel kxt or integral equation, and non-zero function is called the eigenfunction corresponding to the eigenvalues lambda. Do you agree this?
सर फिर से रिपीट कर दीजिए, क्लियर नहीं हो रहा है। सर आपकी आवाज नहीं सुनाई दे रही है.
Yes. Am I audible now?
Yes sir.
Okay. Yes. So eigenvalues, do you got it? The definition of eigenvalues? Okay. We can find the eigenvalues only for homogeneous Fredholm integral equations. Okay. Fredholm integral equation, that equation will be the homogeneous. Okay. Do you know? This is the homogeneous Fredholm integral equation. Okay. Means for the value of lambda for which there is exists non-zero vector, it is also called a function. That function is called the eigenvectors or eigenfunction, and lambda is called the eigenvalues of this integral equation or kernel. Okay. Again, lambda is not the eigenvalues. These are some remarks. If yx is the eigenvalues, then y is the eigenvalue, sorry, eigenfunction of a integral equation, then cx, c any constant, means constant multiple of a function, is also a eigenfunction of that integral equations. And also we know that the homogeneous Fredholm integral second kind may generally have no eigenvalues and eigenfunction. Second kind. Or it may not have any real valued or real eigenvalues or eigenfunction. Okay. So generally, second order, second kind Fredholm integral equation not have eigenvalues or eigenvector. Only because due to the definition of eigenvalues problem, the equation must be homogeneous. Do you agree this? Clear? Any doubt? No. Now we move further definition, that is called the Leibniz rule. Okay, it is the Leibniz rule for differentiation under the integral sign. Okay, Leibniz rule. So what is that rule? This rule say that if f and del f upon del x means partial derivative of be continuous functions of both variables x and t. Okay, both are continuous functions of x and t. Function f and its partial derivative of f with respect to x, both are continuous function of both variables x and t, and let gx and hx also continuous functions, then this expression means how to calculate this integral d upon dx, gx lower limit is a function of x, our limit is also a function of x, and it is a function f which is continuous function of both variable x and t. This is equal to what will do? Just we can write, means we can take the partial derivative of f with respect to x here plus f means upper limit of, you can write put upper limit in place of t here and take the derivative of upper limit dh upon dx minus f x lower limit in place of t and derivative of g with respect to x. Okay, if both are constant, g and h are constant, absolute constant functions, then just it is equal to this one, because this is the constant. If h and g are constant, the derivative of g and h will be 0. So this will be 0 and this will be 0. I will obtain only this. We get only this expression. Okay, so this one is the Leibniz rule. Okay, now any doubt in this Leibniz rule?
No sir.
Now we move a very important formula which is used how to convert a multiple integral to a single ordinary integral. So basically this formula say that suppose we have a multiple integral of order n. It is also called n-fold integral. N-fold integral. Okay, this is also called n-fold integral. A to the power t yt d to the dt to the power n. Okay, is equal to the ordinary integral in this form. Means a to t x minus t to the power n minus 1 upon factorial n minus 1 yt dt. That is, we can write this n-fold integral into the single order integral. It is one-fold integral. Okay, it is n-fold integral in this case. This is n-fold integral and it is one-fold integral. Okay, so this is the formula where you can convert this expression. Okay, okay, please wait. I'm calling. अभी दे देंगे सर, रुक जाइए, क्लास लेने. हेलो, am I audible?
Yes, sir.
Yes, sorry for disturbance. Yes, now formula for converting multiple integral into the single ordinary integral. This one is this one. Okay, so proof is basically, it is clear, just taking the differentiation of this expression and simplified it, you will obtain this formula. Okay, just using the, means we have a integral, this one you can use the theory of differentiation, then you can obtain the solution. You can find the proof of this formula. Okay, now we move a some useful ingredients which will be used in the calculation of or solution of integral equations. Okay, so here there are some gradients, means square integrable functions. It is also called L2 functions, which is valid for this expression. Okay, and inner product of two functions is, it is defined like this way. You know about these expressions. When we discuss the linear algebra, these are the inner product space. Okay, this is the inner product of two functions. This is the orthogonal functions, means two functions will be orthogonal if their inner product will be 0. Okay, and norm of the function is defined like this way: a to b fx conjugate of f dx 1/2. Normalized functions, its norm is 1, and it is Schwarz inequality, it is Minkowski inequality. Okay, so basically these are the results which will be used to handle our integral equations. Okay, now the last, we have a solution. What is the solution of integral equation? So basically a solution of Fredholm or integral equation is a function yx is, okay, it is a function yx here, which when substitute into the equation reduce it to the identity with respect to x. Okay, so what is the function? That function y is called a solution of integral equation. That integral equation may be Fredholm and maybe Volter integral equation. Okay, that equation may be Fredholm integral equation and that equation may be Volter integral equation. Okay, and if we substitute y into the integral equation, then it reduced to identity. If it reduced to identity, then we can say that function is a solution of integral equation. Okay, so here are examples, so that y equal to x e to the power x e to the power x is a solution of Volter integral equation. And Volter integral equation, because it is Volter, because limit is variable here. Yx equal to sin x plus 2 a2 0 to x cos x minus t yt dt. So how to find the solution? So I will try to prove this one, to show this one. So I will show here solution of this equation will be here. Okay, here it is given that yx is equal to x e to the power x is a solution. So it means that if we substitute this into the equation, then we will obtain. Okay, from this we can write this expression yt is equal to t e to the power t. Can I write? Just I have replaced t in place of x and substitute this value into this expression. Okay, what will do? Then we can write here, we can write sin x plus 2 integrating 0 to x cos x minus t, and value of yt is this one, t e to the power t into dt. Okay. Okay, so what will you do? When we solve this integral, then what we have, sin x plus 2 integral 0 to x. I can write t here, and cos x minus t e to the power t into dt. Can I write this one? So we can assume it is the first function, it is the second function, and apply the integration by part formula. Then we will obtain, okay, apply the integration formula, apply the parts of integration, multiplication formula. Okay, first function, and it is second function also we can use. Then we will obtain here sin x plus, okay, after solving this, we will obtain here sin x e to the power x minus 0 to x e to the power t cos t okay, cos t minus x minus, and it is dx minus limit 0 to, so it is t here, it is x minus t here, again 0 to x e to the power t sin x minus t into dt. Okay, and apply the this rule. We have a rule, means integral e to the power ax sin bx plus c dx is equal to nothing e to the power ax upon a square plus b square, and a sin bx plus c and minus b cos bx plus c. Okay, using this formula, basically it is a part of integral formula. When I apply this formula into this expression, because it is sine, and also you can write for cos here, then we will obtain just calculation, just it is a calculation here. Okay, we will obtain here sine plus x e to the power x minus, it will be here, it will be e to the power x by 2 minus 1 by 2 cos x minus sin x, and minus 1 by 2 minus e to the power x by 2 minus 1 by 2 minus sin x and minus cos x. Okay, solving this. Okay, this is your homework assignment, it is homework, and also you can write this one, this is also your homework. Okay, try to solve this one. Okay, when solving this expression and arranging the terms, then just you will obtain this sign will be cancel out, and you will obtain only here x e to the power x. Okay, all will be cancelled, and you will obtain only this one. And it is given that x e to the power x, and I have obtained x e to the power x. So it means that y is equal to x e to the power x is a solution of given integral equation. Okay. It is clear? Just I have substitute the value y in this integral sign. Okay, then solving we will obtain yx. Yx will be obtained x e to the power x. Okay, just substituting y equal to x e to the power x into the integral sign, then you will obtain the solution. Okay, this is the process to check, to show that function is a solution of integral equation. Even not integral equation, it is also process to check, to show the solution of French-Envelope integral equation. Okay, here is this one is the Volterra integral equation. Okay, now I stop here and I'm making the attendance. Please wait. Okay, so roll number 1. Present, sir. 2, 3,
Present, sir.
4, 5,
Present, sir.
6,
Yes, sir.
7, 8,
Yes, sir.
9,
Yes, sir.
10,
Present, sir.
11,
Present, sir.
12, 13, 14, 15, 16,
Present, sir.
17, 18,
Present, sir.
19, 20, 21,
Yes, sir.
22, 23,
Yes, sir.
24,
Present, sir.
25,
Present, sir.
26, 27, 28,
Yes, sir.
29, 30, 31,
Present, sir.
32,
Yes, sir.
33,
Present, sir.
34, 35,
Yes, sir.
36,
Present, sir.
37, 38, 39, 40, 41,
Present, sir.
42, 43,
Present, sir.
44,
Yes, sir.
45. Okay. Please try to solve this expression. I will share the slides to you. Okay.
Okay, sir.